On Argand diagram, the locus of points defined by this equation is a circle. Write down the center and its radius. So when you have the modulus of z equal to a constant, that will automatically give a circle. They've told us it is, but we can see it must be anyway. Now let's just focus on this slightly simpler one. The modulus of z is the distance from the complex number to the origin. And so if it's a constant, it's going to be this set of points. So all these points the same distance away are. We can see we get this circle, and if my complex number was x plus iy, could write it as the modulus of x plus iy, then on my Argand diagram the coordinate's going to be xy, and we can even apply Pythagoras' theorem and see that, yeah, we're going to get x squared plus y squared equals r squared. So when it comes to this one over here, I could rewrite it as x plus 5 plus y minus 12i, and then I can just replace the x by x plus 5 and the y by y minus 12. And this is going to give me 10 squared. And that's the equation of my circle. You could also see it as being a translation of this equation, essentially. I'm replacing my x by x plus 5, so it's going to be a translation by minus 5 in the x direction, which is going to help give us our center. It's going to be minus 5 and then 12. Because when I'm doing minus 12i, that is a translation by 12 in the y direction. And the radius is going to be 10. Show by shading on an Argand diagram the set of points defined by this. So when it was equals, it gave us a circle. When it's less than or equal to, it's going to be everything inside the circle as well. And the center is minus 5, 12. So maybe I'll just I'll draw the axes like this, because we're mainly in this second quadrant. So minus 5, 12 could be, say, up here. And I've got a radius of 10. So we're going to go beyond the x-axis, but not, okay, and actually I want sort of, yeah, I'm going to make it like that. Okay, yeah. So radius of 10, I've gone, yeah, beyond the x-axis here, but I haven't reached the y-axis. So as long as it's, roughly like this, you'll be absolutely fine. And then we're asked to shade the points, so I can shade inside the circle, and that's going to be my answer. I think just one other thing, labeled the radius being 10. Now for C, we're asked for the set of points defined in B, determine the maximum value of the modulus of Z. So I want to go through as much of the circle as I can. In fact, I'm going to draw a new diagram here. Starting from the origin. And the way to do this is to use the diameter. I'm going to start here. I'm going to make sure, here. I'm going to make sure I go through the center, because now I've gone through the radius, and then I'm going to go through the radius again. That must be, that point there at the end must be the maximum value of the modulus of z. As soon as I go sort of up here, I'm not going, I might be going slightly further to get to the circle, but then I'm not going along a chord, it's not going to be as far. So now to find this length, well, I know the radius is 10. So I just need to work out the hypotenuse of this triangle, which has a height of 12 and a base of 5. 5 squared plus 12 squared square rooted is 13. You might actually know that as a Pythagorean triple. So there we have it. The maximum modulus of z is going to equal 23. Finally, in D, we're asked to, we've got a set of points, A, defined by this, and we're asked to determine the area of the region defined by A. So on the right is the locus that we drew in part B. That bit is sorted. On the left, it's a different type of locus. So if you had arg z equals pi, what you do is you draw your argand diagram, and then complex number, basically its argument is going to be pi, and it would therefore be any complex number along this line. Can't be at the origin itself. And if you had the argument equal to 0, it would be going along this line. So what this is saying is it's between 0 and pi. It could be any of this region here. And then the 5 and the minus 20 is just another translation, a bit like we did before. So actually we need to look at the point minus 5, 20. Let's do that. So we've got minus 5, 12. The radius is 10, remember, so it's actually going to be below, let's put it here. That's going to be minus 5, 20. And then we're saying the argument is between 0 and pi, so I'm going to draw a line like this. Just need to confirm that actually it's going to be an open circle at that point, but that's not really going to matter, because for us to want both to be true, we need everything above the line for the argument one to be true, and everything inside the circle for the circle one to be true. Therefore, we are looking to find the area of this region here. What we can do is draw in a sector. So if I can find the area of the sector and then minus the triangle, I'm sorted. So let's figure that out. We're looking at the line y equals 20, and then the circle, remember, is x plus 5 squared plus y minus 12 squared equals 10 squared, or 100. And these 2 points, should be, sorry, I should have drawn it to here. But these 2 points are where to coincide, and therefore I can just set y equal to 20 in this second equation. So x plus 5 squared plus 8 squared is equal to, I'm going to write it as 10 squared. X plus 5 squared equals 10 squared minus 8 squared. Actually, a 6, 8, 10 triangle is another Pythagorean triple, because it's just double the 3, 4, 5 triangle. So we're going to get 6 squared. You could expand it and solve it. We don't need to. It's in completed square form. So x plus 5 is going to be plus or minus 6. Therefore, x is equal to minus 11 or 1. And that's what I found here. The coordinate, this one must be 1, 20, and this one must be minus 11, 20. So I've sorted the triangle because I'm going from minus 11 to 1. It's going to have a length of 12 here. And the height, I'm going from 12 to 20, it's going to be 8. Therefore, the area is a half times 12 times 8. That's 4 times 12, it's 48. Now we've just got to sort out the sector, but again, I can use the triangle to help me. What I need is this angle. Remember, the radius is 10, and I didn't include that before, but that is helpful. So now I'm going to split it into 2. And I could use the 8, but I think I'm going to use the 6 here. So I'm actually going to find out this angle, purple one, and I can double it to get the angle of the sector, and then I can work out the area of the sector. So I'll call this one theta. Therefore, sine theta is 6 over 10. Theta is going to be inverse sine of 6 over 10, which ends up being, I did it in degrees when I did this question, so let me just change. They have been working in radians, so I should probably be consistent. So inverse sine of 6 over 10 gives 0.6435 radians, and that means 2 times that is going to be 1.2870. So then the area of the sector Now there is a little formula in second year A-level maths that's a half r squared theta when you are working in radians, but I'm going to assume you haven't yet done that. So what we can do is take our 1.2870 and divide it by 2 pi, because that is the angle around the whole point, and then times by the area of a circle, which will be pi times 10 squared. And you can see where the half r squared theta comes from now, because that's essentially what I'm doing. Half of the angle times 10 squared. And this gives 64.3501. So therefore, the area of A is going to be the sector, that's meant to be a 0, the sector minus the triangle, which gives 16.350 or 16.4. Well done.